right, let's dig just a little deeper and let me do an example on these P charts or percentage failure charts. Again, from our earlier talk, these are for attributes, so counting occurrence of an event. So C charts and P charts both do this. P charts, though, work when we can calculate the percentage, again, percentage failure. 3 units out of 10 fail, that would be 30%. 2 students out of 100 fail the course, that's 2%. So we would, anytime we can calculate a percentage that we know the failures out of, then we know it's going to be a P chart. So the P chart formula, again, things that we count, monitor percentage failure. Here's the formula that we're going to use. The core formula is down here at the bottom. The upper control limit and the lower control limit. Because when it's all said and done, remember what we're trying to do in these calculations is figure out what our control chart should look like. Then we'll collect our samples and we'll post the sample data to the control chart to see if we are between the upper and lower control limits, and thus our process is in control. Now, what's different, I guess it's very different in the P chart, is that when we're calculating our upper and lower control limit down here, P is our percent that fail normally in our process. If we don't know what that is, sometimes that's specified by the machine we use or things like that, but if we really don't know, which is often the case, we'll just take many samples and say, well, historically, this after this sample, after this sample, after this sample, and it's almost like the old grand mean, where we'll take the mean of the percentage failures across many, many, many samples, and we'll assume that to be the percentage failure of the process. Z is our same old Z, but I'll show you a little bit of a trick with Z here in just a minute. And then this is a standard deviation, and this is where it gets really important. We have to make this adjustment in order to calculate the standard deviation of the process. So if our percent failure of the process either is given or we estimate it based on many samples and we say it's 2%, you have to calculate that to a decimal. Transform that to a decimal. That would be 0.02. That is what goes into your formula. And here, you cannot put 2 into here. You have to put 0.02. So make sure you're using the decimal equivalent. N is your sample size as always. So the 2 mistakes students always make with this problem are, 1, they don't use the decimal form, and number 2 is they don't take the square root of the entire fraction. Sometimes they just do the top, or they forget to do the square root at all. So it's not too bad. And then, of course, with the lower control limit, it's just the minus instead of the plus. So that's not too bad. I want to run through and set up this problem at least. Here's a sample. The defective rate for your process is 1.5%. So the P is given in this case, 1.5%. I immediately translate that to a decimal, 0.015. That's what I'll use in my formula. And I know that my upper control limit equals P plus Z of, and I'm going to go ahead and do the full blown, there we go, P 1 minus P over N. Developed a control chart for the 99.73 confidence, or 3 sigma, and the sample size of 500. So let's put some of these numbers in here. I'll let you actually do the calculations. P is 0.015 plus, it says use a Z of 3. And then we're going to fill in this, the square root of 0.015 times 1 minus 0.015. I know it's a little tedious, but it really does work. Divided by N, which in this case is 500. Put that all into your handy dandy calculator, and then the lower control limit is the exact same thing, but we'll use the minus sign, minus 3 times this same operation. What I want to take a second and show you, though, is that these z-charts can be a little confusing. And if you click on one through the software or you look up one in Google and you ask for a z-table, you could get many different things. And you have to be really careful that you understand what you've received. So it'll always look like this. It'll show a normal distribution. But the important part to look at is what part is shaded. And I know often in the textbook materials, they'll give you a z-chart that looks like this. And this portion in here will be shaded. What this is telling you is that when you go to your z-table down at the bottom, that the z-value only represents this portion of the distribution. That can be a problem because when we're doing, let's say 95%, the 95% is actually the entire middle of the distribution, not just one side. So I always have to check the distribution to see if it's for the whole portion that I'm interested in or half. And if it only gives you half inside the table, you have to divide your z by 2. Sorry, I've switched to a better color here, my mistake. We switch it to 2, so it would be 0, went thick on me, sorry, let me, there we go. It would be 0.95 divided by 2 equals what? 47.475, I believe. That's the value, 0.475, that you look up in the body of the table, and then you follow it across and you follow it up to obtain your z. In the case of this problem, we don't need to do that because I provided that we're just going to use a 3 sigma z. But if you're doing the homework problems, it may only say, oh, use a 99.73, and if the table only covers half, then you'll have to divide that by 2 and look that value up in the table. The other tricky thing that sometimes shows in the homeworks is they'll say use alpha, A-L-P-H-A, of 0.03 or 3%. What that means is alpha is the opposite of your confidence, so that would be 1 minus 0.03. They're really talking about 97%. So if they use alpha, then you got to subtract that to get to what you're really looking for. Sometimes they'll just say the percent. Sometimes it'll just say the 3 sigma. Use this if you have it. Otherwise, you'll have to manage one of these two. All right, let's give it a shot.